Thanks. So I'm Susannah, as Eric said. I'm here from Sydney, where our Maps API team is located. And I'm the tech lead for the Maps API version 3, which is our new version of the API that we launched a little more than a year ago and brought out. It graduated from Code Labs just last month. And we created this new version of the API after a few months of investigating our issues of performance on mobile with the older, or then current, V2, version 2 of the API. So the Maps API, for anyone unfamiliar, is a product that allows third-party sites to embed a Google map on their own website and customize it. The map is embedded programmatically and can have overlays and markers added as necessary. You can control where the map looks and how it behaves with the rest of the site. So we wanted to bring this to the mobile space as well. But we discovered in our early investigations that the API was maybe just not going to work for us there. I'll get into a little more about why. First, though, I will share with you the experience of Maps API version 2 in 2009. So that was 17 seconds. This is how long it took over a 3G connection to load that map. And you could see after 10 seconds, it turned gray. So that was a good first step. You knew something was happening. And then 7 seconds later, we actually got the map to show you. This is, we would ride around town and just try it over and over again on an iPhone running OS 2 to see how we were doing. So today I'm going to talk to you a bit about latency, how we've measured it, and what we've done to reduce it. The architecture that we've used to help us, the architecture of our JavaScript in particular, that we've used to reduce latency, and then some other optimizations we've made to get that map to appear to developers as quickly as possible. Now, our maps are embedded on other people's websites, so there's still more for a developer who's using the API to do to reduce the full latency of their page. But we think it's really important to get the map there as quickly as possible, particularly if you're writing an application that is solely a map. So examples of how the API is used, sometimes a map is just one component of a page. Sometimes it is the whole application. For example, a campus map that's designed to load both on the desktop, but also on a mobile device. So we're striving for this one solution across all devices, all browsers. Loading quickly is the key part. But to understand latency, we need to first define what we're talking about. And the way that we've defined it for our team is to split it into the user-perceived latency. This is the time it takes for the core components of the page to show up. In our case, this is the map imagery. Then there's the page ready time, which is when the page is actually usable. And for us, this is when the map is draggable and zoomable. And then the page load time we've defined to be when all elements are present. So for us, this is when the controls are there, so that you can change map types, the logo shows up, the copyrights are there. These things that are not essential to using the map, but are essential to use all components of the map. For user-perceived latency, this is what we've really seen as the key thing to reduce. That just for the user to see the map imagery there and start understanding and processing what's happening on the page, that even before you can start dragging it, they need to understand what they're looking at. So we really want to reduce this when the user perceives the page to be ready. So breaking down what happens when loading our API, I have this chart for you, where first we download the bootstrap. This is the script tag that a developer embeds on their page that loads an initial small JavaScript file, which will then download the rest of the API. This in version 2 is a 15 kilobyte file, or 4 kilobytes compressed. It loads then the correct version of what we call main.js, which is the public interface. This file is 180 kilobytes in version 2. It's 65 kilobytes compressed. This is a large file, but it contains the full interface and the functionality that is required to perform the functions that are available in that interface. Then the user's code is loaded, at which point they can initialize a map. And it isn't until they have instantiated a map that we know where the map will be centered, what zoom level it will be at. So we can't start loading anything related to the map until this point. So when I showed you where the map turns gray, at this point, the map would have been initialized. We know what div the map is going to be in. We can turn it gray. But only at that point can we start figuring out which tiles we want to show, which map imagery we want to show. So once the developers told us what that center and that zoom level is, we can start loading images. And to show a 400 pixel by 400 pixel map, it takes approximately 6 25 to 30 kilobyte images. Then in delay loaded code, we actually initialize the drag. This is a small file in version 2. So in order to reduce latency, we need to measure it. So we needed to figure out what was the slow part in that whole process. Well, on desktop, it's simple, pretty much. We've used HTTP Watch in Internet Explorer for quite some time to understand what's happening, and we've made a lot of optimizations on maps.google.com looking at the breakdown, the waterfall charts that we all have heard a lot about over the last 2 days. But for anybody who's developed on mobile, you know that it's never quite the same as desktop. Starting with the fact that there is no really simple waterfall tool like HTTP Watch that just works seamlessly with mobile. So what we did a year ago is use the iPhone configuration tool, which allows you to go through a proxy on a 3G network and set up a server that we could access over that 3G network that was running a Fiddler instance. And we proxied all of the requests through this server. So this slowed down the request somewhat, but let us see what was happening in terms of JavaScript. And we captured the download times of the entire map loading process. And what we really noticed were these two areas, which follows a JavaScript load, and is this time between when the JavaScript is finished loading and when whatever component it's downloading is actually able to begin downloading. This is the time that it takes to parse and execute that JavaScript. And this blew us away how big this time was. This was on OS 2 on an iPhone, and it was just seconds that we were waiting for these files to load. And if you recall, we were loading that initial interface, the thing that allows somebody to say new map and actually create an instance of the map, was 180 kilobytes. So running these tests, we then ran tests that where we loaded different file sizes, and at the end of the load of the JavaScript, we would load an image to track how long it took us between the finish time of the load of the JavaScript and when the image began loading to figure out what that parse and execution time was. And recent tests have shown that this is around 1 second per file plus about 5 milliseconds per kilobyte. This is a big improvement over what we saw a year ago on OS 2. It's also an improvement on what you see on older iPhones running OS 3. We haven't yet run it on OS 4, but I expect that that's going to be a continued improvement. We've seen on both iPhone and Android huge improvements with every OS and every software and every hardware update. The time to load, to parse and execute this JavaScript is linear or even super linear as you get to larger and larger files. So our 180 kilobyte file is here on the right end of the chart. And we can see that even today, it would take 4 to 5 seconds. And a year ago, it would have been more like 7 or 8 seconds, which is why it took so long for the map to even turn gray in that initial example. So then we needed to figure out how to reduce this. And we were in this interesting situation of being an API, where we've promised developers that our interface will not change and the functionality will not change. So here's a breakdown again of what we were downloading. And what we really saw as the place that needed to improve was loading this main interface. And we did everything we could to pull out components of it and to delay load as much as possible. But we made so many promises to the developer in terms of synchronous function calls that just limited what we could actually move out of that file. And this is where we decided it might be time just to have a new API. The API at this point was 4 years old. It was filled with extraneous things, and there'd never been a decision at the beginning of what it was going to look like 4 years later. We didn't know what features were going to exist on maps when the API was first written. We did first, though, look at some typical attempts at how to improve our loading time. We've relied on caching heavily on desktop browsers for years. Because we're a popular API and we're used across many sites, we've been able to take advantage of the fact that the JavaScript and the map imagery, the tiles, are frequently already in either browser caches or proxy caches. But on the mobile device, the cache is far more constrained, with file size restrictions and the total size of the cache being limited. This is also something that's improving with each OS update. Last year, there was, on the iPhone, you could have something like 20 or 25 items of about 20 or 25 kilobytes uncompressed in the cache at any one time. We've been able to cache many larger and many more files than that now. But the cache is still cleared more frequently. So though we're still benefiting from the proxy caches, we can't really count on the browser cache on a mobile device. So we looked at the HTML5 database, or app cache. This is great for storing data within a site. It's very difficult to use cross-site because you don't have control of the manifest. And for us, our data changes so frequently. We're always pushing new versions of this that there's no one constant URL that can be specified as the resource in the app cache. So great for standalone sites, not good for the API. And we, of course, were using compilers to obfuscate our JavaScript and to optimize it for code size. So examples of compilers are things like Clojure or Gwt and many other tools. And these will take all of your beautiful, long, verbose variable names and method names and shorten them to small 1 or 2 character names. So we were doing this already. So we'd done we'd looked into the regular approaches to these things. We also were already spriting all of our images. And we try to combine our JavaScript files where possible. So we have a delay-loaded module system, and as functionality is required, the module for it is downloaded. But we saw that there's that huge overhead in parsing and executing each individual request. So we use, on the client side, we bundle our module requests and have server-side code that handles a single request from multiple files that will then find the files and concatenate them together and send those down. This we've seen by reducing 3 requests in the API of 15 to 25 kilobytes each down to 1 that's about 60 kilobytes. We saw incredible speedups on mobile devices. But we needed to take that 180 kilobyte file and get it smaller. We'd done all the other things we felt that we could. And we were going to write a new API, but we needed to figure out what we could do to still provide the same functionality without the big bloat, with all that code. So we chose to, with the goal being fully to reduce the size of this main file, that public interface. So we chose to use a model view controller architecture. In this, that main file consists solely of our models. The models are simple state-storing objects. They can be created by the developer as an object that then can have all of the same types of functions called on it, but they don't do anything. They just store state. So they do things like store the center of the map, the zoom level of the map, the position of a marker, but they do absolutely nothing with it. Instead, we asynchronously load views, and our views and controllers to work with the two. We asynchronously load the views and controllers that then do all of the heavy lifting. They do all of the DOM rendering, all of the computation. There's no computation in that initial interface. And there are no synchronous promises made to the developer anymore. This does complicate writing applications from time to time, but it uses an event-based system, which is fairly familiar to JavaScript developers, as opposed to other approaches that could have been taken using callbacks, which tend to be, callbacks and closures tend to be far more difficult for our developers. So the initial download contains only these tiny models, which can be a few hundred bytes. So adding a new feature adds a few hundred bytes to the API and doesn't slow down the load significantly. Here's what it looks like. So in the case of a marker or an info window, the model stores a position. This is in lat-long space. We then have this controller that knows how to convert between lat-longs and DOM pixels, because of course the lat-long isn't necessary at all when you're actually rendering something in a DOM. We then have a view that knows how to render things based on a pixel position in the DOM. We bind these things together so that the position controller's lat-long position is bound to the model, and the view's position is bound to the lat-long, or the position controller's pixel position. When the model's position changes, the controller is notified. It then does all the calculations required asynchronously. It sets its pixel position based on the conversion from the lat-long position. The view is then notified, and the view can do whatever it wants when the position is changed. In the case of a marker or an info window, it means it re-renders itself in the DOM. So code-wise, so the marker stores this position. The developer creates a marker, and it gives it a position, and it gives it a map. We then, in the marker model, respond to the map change. This is the syntax you see here is sort of this just sort of neat code optimization we've made. It's just an event-based system, so an event is actually triggered and calls this method, but it's a little easier to write it this way. So when the map changes, the marker model requires the views module, calls this initialized marker view. The view passing it itself. The view then looks and says, oh, there's a map. I'm going to add myself to this map, and I'm going to bind all the necessary properties, and I'm going to render myself in the DOM. But this has all happened asynchronously, and all the developer has had in their first download is the ability to create a marker and to call setMap and give it a position. So the view gets initialized, and then when the marker view is notified that its position is changed, which happens on binding, it renders the marker. So as a result of this architecture, these models being downloaded synchronously in the initial interface download, and our views being loaded asynchronously, we were able to reduce by chance, we reduced that bootstrap load from 15 kilobytes to 4 kilobytes. We were able to reduce the 180 kilobyte download to 33 kilobytes. We were initially aiming for 25 kilobytes, thinking it was really important to be able to fit in the iPhone cache. Realizing how frequently it's cleared, we realized that really wasn't either realistic or necessary, especially given that a year later, a 33 kilobyte file fits in the iPhone cache with no problem. So that architecture directly led us to be able to have this tiny little interface file that is downloaded. It does mean that much more has to be downloaded on the fly as we go, because there's less downloaded up front. We still, though, have to wait for the developer to set the center and set the zoom level for the imagery to start loading. But we want to, when they do set those properties, we want to load the imagery much faster than we are. So, this is the next part that we needed to optimize. was this downloading of map images. We've already shrunk the time between when the developer has requested the API and when the map shows up. But we need to, or when they can tell us where their map should show up, but now we need to reduce those 6 files that are 30 kilobytes each from being downloaded. So to do this, we've taken advantage of our static maps API. This is another API where you just get one image that is of a fixed size. It's an image, you render it in an image tag, and it cannot be dragged or zoomed, and it fits the size that you've requested at the center and zoom level. So when we get the center and the zoom level from the developer, and we know the size of the map, we send off a request for this image. And this image comes back, because it's one file and only 40 kilobytes, it comes back much faster than our six 30 kilobyte files. We load that in the map div, and then as the tiles turn up, and as the rest of the JavaScript turns up to make the map draggable, the static map first becomes draggable, and then the tiles just overlay seamlessly on top, and you don't notice that this has happened. So it does mean that we're loading the same pixels twice for that initial load, but it has reduced the time to load a map by seconds on the mobile device. So here we took the 6 30 kilobyte images and instead load one 40 kilobyte image. It also means that we're loading that in parallel with the drag initialization. The drag initialization has increased a lot, but because what we were trying to do was reduce user-perceived latency, and that is the time at which the imagery shows up, we have reduced that user-perceived latency, though perhaps increasing or remaining the same, that time to actually have the map be draggable. It turns out it is still faster because everything is smaller overall, but there is that perhaps a bigger gap between the user-perceived latency and the page load time. So a slight variation that's been used on maps.google.com. We know the center and zoom level of a map on maps.google.com. We know there's a default viewport when you load maps. Because we know that default viewport, we can start sending down the tiles immediately. We don't need to wait for everything to load before we get told the center and the zoom level and the map type. We can just send down the tiles right away. We call this inlining the tiles, but it's also a form of prefetching. What I left out here, once the size, we don't actually know the size of the map when we first send down all of the maps.google.com code. So we send down the middle tiles, the ones that we know will be shown. And then if the map is larger than that, we fill in the rest of it. So this is a form of prefetching, which is great for latency. It's really great if you load everything before, once you've loaded the important stuff, and then you start loading all the things that the end user might look at later. It's really fast when they then load those things. This is bad for users with limited or expensive data. And I think in the US, AT&T just stopped having unlimited data, so you'll probably all start caring. We've never had unlimited data in Australia or New Zealand, so we've always cared. So be nice to your users. Prefetch with caution. Prefetch when the chances that they'll use a particular thing is really, really high. So in the case of maps.google.com, we know that those 4 center tiles are going to be shown. And so it's safe to prefetch those or to inline those. So you can see that was a lot faster than our 17-second load, but there's still a lot more work to be done. And we're lucky because each release of Android and iPhone has made that faster, just in and of itself. We'll also get faster as our JavaScript, we're a smaller API still than the older version, v2. So as our JavaScript finds its way into proxy caches and local caches on the desktop, we'll see ourselves continue to get faster. But there's still more we should be able to do to ensure that we're optimizing each step along the way for loading browser applications on mobile devices. So I'm happy to take questions now. Also, my colleagues James and Josh will have a whiteboard session at 3:10. I'm not sure where the whiteboard session is, but they'll be talking more about what we've done on Google Maps itself, on maps.google.com. We have a whole team, another whole team of people devoted to speeding that site up. So they'll talk about a lot of their findings. So if you'd like to ask any questions, I invite you to come to the microphone up here at the front.
Well, we've got a few more minutes here. So do you have any other insights that you found in the course of developing the UI that you think would be helpful for other people in the audience interested in mobile development?
Let's see, insights. I guess we have also done a lot of work, so more on the mobile side than the latency and fast side of things. We've done a lot of work in looking at graphics options on the different devices and how to make this a truly cross-platform API. One thing that we recently did actually was we launched Street View in May, and we launched it in a fully HTML version. There is no Flash in the v3 Street View implementation so that it can run on mobile devices. And this is something that not all browsers are supporting HTML5 and Canvas yet. Not all support it fast enough yet. But we've seen really impressive performance on our WebGL implementation. Lightning fast. I believe my colleague who implemented most of this actually had to slow down some of our animation using WebGL. Whereas on Canvas, it's pulling teeth to try to get it to be fast enough. So that's sort of exciting stuff that we're working on. And with that, we've had to look at Canvas, SVG, and VML, and what works on which browsers. I gave a similar talk at Google I/O, and there was a section from my coworker who did the Street View implementation and has looked at all the graphics stuff. If you're curious about more, I invite you to visit that, particularly that half of the talk. Yeah, a question at the microphone, maybe.
Hi, Charles Shopzilla. Are you guys evaling any of your JavaScript on the mobile side? Bringing it in as a string and evaling it later? Is that costly?
So we aren't currently. I believe we've looked at some of this and particularly with images as well, storing images as data and getting those on, and then dealing with those on the client side. So I guess each of our modules is evaled at load time. But they are sent down as actual JavaScript files, not as strings. I forget what the results of these were. We did look into a lot of this a year ago. Yeah. Sorry.
Anyone else interested in asking a question? Great. Well, then why don't we take a break, and the next talk will be on the Meebo toolbar. Thanks, everybody, for coming.